All right, so today I'm going to be talking to you about GIS remote sensing, and I added in my hazards work that I've been doing for a while now, because a lot of people have a hard time understanding and putting into context what GIS and remote sensing can do for you. So what I want to tell you first is, who am I? You can't see my face because I got a mask on. So this is what I look like without a mask. This is fluorite, by the way. I used to be a teaching assistant for geology, and I loved my room, so I would take pictures of myself all over the place. My name is Jackie Cooney. I am a geography graduate student downstairs, and I'm studying geologic hazards, specifically sinkholes, obviously. I have a certificate in GIS from Harper College, and I am the TA here on campus for GIS and remote sensing. I am the former TA at Harper College for geology, astronomy, geography, and GIS. Yes, I did all of those at once while a full-time student and holding down 2 jobs. I've also interned for the Cary Police Department in Cary, Illinois, doing hazards analysis, and EOP stands for Emergency Operations Planning. And most recently, the Palatine Emergency Management Agency for GIS. So I did their mapping for technical search and rescue. So what is GIS? You'll be happy to know that there is no concrete definition for GIS. So there's no universally accepted definition. You can't look it up and get one definition, put it on a test, and be like, okay, that's it. But all definitions have something to do with computer software that visually represents data and forms models and maps. Okay, so it's visually representing everything that you guys are going to be doing out in the field. It can also visually represent financial data, if you want. It can visually represent the coronavirus. You've seen that big old map that Johns Hopkins University has, that dashboard. I know how to build that. I can build that from scratch. This is how you do it, is with GIS. There are 3 approaches to GIS, and keep this in mind as you work in the field. The first approach is as a developer. So developers look at GIS software and they think, how can I make this better? We do this all the time. We might build a model that might need to be integrated into the GIS system. We might need a bug fixed. We've all had bugs on our phones, right? Or on our laptops, and we're just like, why don't they just fix this? That's what developers look at this. It's an evolving software. We can also look at it as an application. This is a tool to tell a story, right? This is a tool to tell us about cenote hazards. What's happening with groundwater in Quintana Roo, right? We can tell a story about anything we want with GIS. I did a final project on location of bookstores in rich and poor neighborhoods. Why? Because I could. And then there's the scientific approach. This can also be called GI science. And that's what we're primarily going to be doing. We're going to be collecting data, accurate data. We are going to be using our interpretive skills, our cognition skills, to be able to build models, build maps, and be able to tell stories to people who might not have that degree, might not understand the science, right? So that's what we're going to be doing. That's what we're using GIS for, is to tell that story to help them live better lives. Is GIS the same as GPS? No. No. I'm glad to see that you shook your head. I'm proud of you. But they are related, okay? GPS puts the location data into GIS, right? So I know my students are going to be using GPS data a lot. I don't know if all of you are. But when you do use GPS, what happens is that data, you get to record that data, you have to put it into a database so that GIS knows where you're working, right? Because if you don't put any location data in, it's not going to show you anything, it's just going to be a blank screen, right? You need to know where you're working. Then GIS takes that data point and says, what do you want me to do with this? How do you want me to visualize this? Do you want me to make a 3D model? Do you want me to just show you a 2D map? how do you want me to use this data? And then you teach GIS how to use the data, okay? So what does GPS do then? And why am I talking about GPS? I thought this lecture was about GIS. Good question. I'm sure you were asking this. Well, GPS is what you're going to use to get the location data so that when you go and use it to write your papers, do your posters or whatever, it tells you where this is happening, right? Now, you might think, oh, I'll just trust the GPS. I'll take my phone or I'll take my GPS receiver and be like, yes, okay, it's wherever I'm at. No, no. You need to know how this works, because if you don't know how this works, you won't have accurate data. How GPS works is that it uses a method of triangulation. So as you see here, we have a method of 3 satellites overlapping at one point here. That gives you the most accurate data. And why it's important for us, specifically, where we're working, so there's a lot of tree cover, right? And trees kind of block that GPS signal. So you kind of have to wait. Satellite here now? Is it here now? Is it here now? You gotta wait, or you might move a little bit, or move up a little bit, or move back a little bit, until you get 3 satellites. You can't use 2, because that won't be the most accurate data, okay? So triangulation, you can also use triangulation for earthquakes. You might have heard about that, maybe in a Geo 101 class. That's how they figure out where the epicenter of an earthquake is. But they use it the same way here. And as you see, we have 4 satellites here, but only 3 of them can be used because only 3 of them converge. If we were to use only 2, notice there are 2 possible points, right? You need that 3rd one to tell you for sure. Okay?
And then the satellites move, and so you
Yes.
get like 6, and then all of a sudden the satellites all move, and the
Yes.
tree now covers them up, and then you drop down to 2.
Yep. And then you gotta wait again. There are a ton of satellites, GPS satellites up in space that are moving around the Earth. So eventually you'll pick up another one. You just gotta wait. Take that measurement when you can. So how do you use a GPS? The reason why I'm telling you about this is I had a very unfortunate field experience when I was in paleontology. The people who were in charge did not calibrate GPSs. And I fell, got injured, lost my radio, and GPS didn't work because it was calibrated for Kenosha, Wisconsin. Couldn't find my way back. Oh, I know, right? So I had to use my wits about me and my spatial reasoning skills to figure out a way back. I don't want that to happen to you. And we also want our data to be accurate, right? We don't want it to be calibrated for DeKalb and we're in Mexico, right? So you need to calibrate for your region, and that's what's happening here. You have all of them that are using their GPS receivers in one location, right? You're supposed to put it on a higher elevation, as high as you can, but we all know that we're not going to have really high elevation, right? So you put it on one place, all of them in the same place. Make sure you have 3 satellites, and let it sit there for a couple of minutes. Make sure it calibrates to the region, okay? That's for your safety and for the accuracy of your data, okay? Know the projection you're using. That's super important. I'll talk about projection in a little bit. Okay, we used, when I was out in Montana, we used universal UTMs, universal
Transmercator.
Yes, Mercator. I get tongue-tied for whatever reason with that every single time. Or you can use WGS 1984. Now, if you're using GIS, a lot of our data is going to be in either WGS 1984, NAD 1983, but you can have it in UTMs. UTM is going to be a projection, and that's going to be different than what WGS 1984 is, okay? Constantly save your waypoints. Waypoints are markers, right? Okay? Constantly save those. Because if you have to track where you've been and which cenotes you've been and where you have collected what data, you want to make sure that you can get back to where you were, right? Super important. Cannot stress this enough. And allow the GPS to track your path. Let's say you took data at a cenote. You start walking back and you're like, oh crap, I forgot something. I forgot to get whatever measurement. Well, now you know you can go back exactly to your site and get that measurement and go back. Okay?
Question.
Yeah.
The
Yeah.
UTM is a PCS system, right? Projection coordinate system?
Yes.
Okay.
Yeah, I'm going to be going over that in a minute.
Okay.
Ta-da! It's like you're psychic, man. Okay, so how do GPS points get transported into a GIS program? Great question. So, GPS calculates points in a geographic coordinate system, okay? This is going to be in degrees of arc. We already know longitude and latitude, right? Little degree markers, right? That's not temperature degrees, that's degrees of arc. Arc is a distance on a sphere or a circle, okay? That's drag for you. Not a fan of drag, but that's what it is. These are two very common geographic coordinate systems. NAD stands for North American datum. This can only be really used for North America for super strict purposes. This is for world geodetic, so you can use that for the world. But, so what happens, your GPS records those measurements, okay? And that's on a sphere, as we see here, right? Spheroid, not a true sphere, but I'm not going to get into that. And then you put it into your GIS system. You'll have a database, it could be an Excel file, it could be whatever. You put it into GIS, and you notice it doesn't map right. Why doesn't it map right? Well, you're trying to map what's on a sphere on a 2D surface. Has anybody ever, like, I don't know, ripped off the skin of an orange and tried to put the orange back together? No one's a dork? Okay. So have you tried to flatten out the orange skin?
Yeah, always like bends.
It always bends, right, and it never goes back together the way it's supposed to. And then you get these weird creases where things shorten and then you have to elongate it to try and get it right.
Yeah, and they don't fit.
And they don't fit. That's because you're taking something that was originally a sphere and you're trying to make it flat into a 2D surface, into a 2D map. And it doesn't work. So we have to project it. We have to change these degrees of arc into linear units. Linear units being meters, feet, miles, kilometers, okay? So this is just the flat version of GCS. And how does that work? Map. Usually matrix map. But GIS is fantastic. It does it for you. You just tell it what to do. If you wanted to transfer NAD 1983 to UTMs if you wanted to, it'll do all the math for you. You don't have to do it by hand. I tried doing it by hand once for a project I had to do because it wasn't switching over. That was the worst thing I've ever had to do in my life. I never want to do that again. Please don't ask me to do it again. I had to actually translate something that was, that's supposed to be 1984, not 1894, WGS into NAD 1983 and then transfer it into UTMs, which was really hard. Mel, do you use UTMs or do you?
I've used both.
Okay.
I mean, yeah, I've used all of it.
Okay, so you don't have a strict guideline on which to do?
Yep, because
Okay.
you can always translate, like you just said.
Right.
We can translate back and forth between them. As long as we know what they are,
Right.
it's fine.
Okay.
And then technically North America, is Mexico considered North America? I mean, technically it is,
yes,
so
yes.
we can use NAD.
Yes, but anything south of that, you know, like when you get closer to like Colombia and all that over there, I don't think you can use that. I've never seen data from there, so I don't know if they use NAD 1983.
Because usually we use WGS.
That's usually a more stable
Yeah,
one.
84. That's the one we usually use down there.
Yeah.
But Because they usually use the NAD when I'm here.
Right,
Down there. But I don't care.
okay. I went on a field camp once and it was strict UTMs only. And so I was like, I'm not sure if you guys have that strict. Okay. So why
Any
does,
GIS person I've met is like committed to one or the other.
okay, as long as we know.
Yeah.
So why does GCS and PCS matter? So this is one of the maps that I had to create for search and technical rescue. I just wanted to give you an idea of what this looked like. Measurements are calculated differently depending on which projected coordinate system you use, okay? They all have different origins. You remember the Cartesian coordinate plane, right? Where you have the origin at 0, 0, and you have, you know, a whole bunch of quadrants and everything like that. Not every projection has the same origin, okay? So you need to know which origin you're going to be working with, I mean. And the parallels are going to be different. So the bounds to use for the projections are going to be different. So if you're centered in North America, like in the United States, your bounds, your parallels are going to be different. Your origin is going to be different. If you want to show the United States as best as you can without distortion, without making Illinois super bigger than Texas, because I'm just saying, you want to make sure you're using a projection that shows it accurately, right? And different projections will have different distortions. It might show size really well, the area is off, you know, it magnifies area, or it shrinks area. Or it makes it really long, but it also makes it squishy on the sides, okay? So your projections are important. And the reason why your parallels are going to be different in your origins is because the Earth's surface measurements are going to be different, right? The Earth isn't a perfectly smooth sphere, right? It's bumpy. And it's not a perfect sphere either, it's a spheroid or an ellipsoid, okay? This is super important. Your projection is super important for things like hazards analysis, search and technical rescue, emergency management, and the military. Anything having to do with human lives, super important. Because if you say a cenote is over there by that door, but you use the wrong projection, it could be off by this much, or over there even. But even a small smidgen off can affect someone's life. Hence over here, like with this map, if you're looking for someone in this forested area, in this wetland area, a meter off can be life or death. So that's why it's super important to understand what projection you're using and to make sure that it's as accurate as possible. So in our research down in Mexico, for hazards specifically, you need to be as accurate as possible, because if someone's buying that land to build their house and they build it on land that has said, no, there's no cenote there, and then they go and there's a cenote, they can't build. Or if they built it too close and they trusted our measurements and their house falls in, that's a big problem. Yeah.
So I'm sure you had to use a couple of geodatabases there, like, did you use like reliable sources then, like, or what sources did you use?
Oh, good question. I built this.
Okay, so did you have to do like collect data then?
Yeah, so some of the data, okay, so this was a really hard project, believe it or not. This is a small map, one of the harder projects I had to do. So what I did is I took satellite imagery and digitized all the stuff. Then I had to make sure where the wetlands are and where the little ponds and lakes are. Those constantly change in the wetlands. So I had to keep track of what was changing. So the data that I was originally given showed it was all over the place. Like, this trail is going off of here, this trail is going off there. Nobody had checked it. They just was like, automatic digitizing, yes, it's great. It was way off. This one took me a whole week just to get some of it, half of it done.
Yeah.
So, and then the contour lines here, oh, that was a pain too, because I only had 1 foot contours, and these contours are supposed to be 20 feet. So I had to subtract individually the contours in between 1 and 20 feet. So painful. I am not kidding. But I did it.
But you also mentioned like ground truthing. This is part of the reason like Jackie's not going down with us, but we're gonna go ground truth things. So you can do so much on the computer and so much with data, but you really need to go there
Right.
and see and prove that that path actually goes that direction.
Exactly. Because like what I'll show you later is that we can look at remote sensing data all we want. And it's pretty nice, but the resolution is terrible sometimes. Resolution meaning that it's accurate up to 10 meters, up to 50 meters, up to 30 meters. So that's a lot of distance, right? So we need to make sure that what we're seeing in the remote sensing image is actually what we're seeing on the ground. What is remote sensing? Nice segue, by the way. So we use satellites to scan the Earth's surface, and there are two different ways to do it. There is a passive and active, right? So passive is this top one, where we just read the sun's rays bouncing off our surface. We just gather that through a sensor. Or we have the sensor project rays onto the surface. And what we get out of it is a bunch of bands, what we call bands, wavelength bands. How many of you remember the electromagnetic spectrum? Roy G. Biv, you don't remember him? Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet, no? Okay. So Roy G. Biv is the visual spectrum, what we can see, right? Outside of that, we have X-rays, UV rays, gamma rays, all that other stuff, right? These sensors, there'll be like a suite of sensors on there, and it can pick up each one of those bands. You don't have to use all of them, of course, but it can pick them up, okay? Remember you were asking me about thermal bands? Thermal band is 6 on Landsat 7, I'm just letting you know. So they give you spectral data, like I just told you, the different bands, and the different bands will show different things. Okay, and I'll show you in a little bit. You have spatial data, it also takes coordinates, right? And then you have temporal data, time. What time was this taken at? Was it daytime, nighttime? Seasonal time, winter, summer, right? All of that is found in remote sense images like Landsat, Sentinel, MODIS, Globus, Copernicus, a whole bunch of other ones, okay? And they come in little, looks like a square like this, and they got little pixels. We know what pixels are, right? Yes. Sometimes they are the bane of our existence, right? Well, each pixel will have the spectral data. So it'll have the color that we're looking at, right? And that,
It is 12:15, we do need to,
Oh, I'm sorry,
yeah,
okay,
no, we don't have like,
okay.
so, let's, yeah,
Yeah.
perfect.
Hazards, risk, and vulnerability. So hazards, just letting you know, is the potential event to cause great problems. Risk is quantitative or qualitative likelihood of the hazard happening. And vulnerability is the susceptibility of a community to experience this, okay? This is kind of like the hazards thing that we saw, the vulnerability map that we saw yesterday in the video, okay? As you can see, red being severe, green being low. For remote sensing and GIS, this is actually one for vegetation, but as you see, all the black stuff, that's water. So we use the vegetation bands to be able to see where the water is, okay? It's kind of nice that way, because water will absorb those thermal bands. This is going to be near infrared, infrared, and shortwave infrared. Then we could use that data to make sinkhole testing sites and training sites, okay? We need ground truth for this, because as you saw in that other image, yeah, there's a bunch of black stuff there. But we need to make sure that that's not a shadow, that it's the actual water, right? So we need to gather that data, put it in GIS, and then have machine learning to decide if it's actually going to have a trend, a sinkhole trend. And then these are the susceptibilities. Susceptibility isn't as accurate as quantitative analysis, which is numbers, actual numbers, okay? So what are we gonna do? So we need to measure the cenotes using photogrammetry, which is just measuring and then translating what it would be in ground truth measurements, to see the health of vegetation and to see if any vegetation is going to be affected by cenotes collapsing or the development of cenotes, or you could even do to see if the cenotes that are polluted with all the stuff that we've been talking about for the last couple of days, see if the vegetation around there is affected. And then this is going to be the measurements. This is photogrammetry, and then we do it in real life, okay? This is ground truthing that I already described. These are the things that I look for in sinkholes, but I'll talk to my student about that more later. Oh, someone's taking a picture, I gotta wait.
Yeah, no
Okay. So why do I talk about vegetation health? Because a healthy vegetation will have green, it'll give off nice light and everything like that, it'll be real bright red. If it's stressed or polluted or sick, it won't have as healthy of a vegetation. So that's why I'm thinking maybe we might be able to see unseen cenotes by the stressed vegetation. Or maybe we can see cenotes based on species, because each species will have a slightly different fluoresce. And that's this here in Montana. Okay? So what are we looking for? Can we determine cenote location based on vegetation, health, and species? The purpose is to help researchers and emergency managers identify areas. Oh, sorry, I was in the way.
No, you're in the picture, that's why I won.
No! Based on, if they can see where sinkholes are using remotely sensed images without actually getting to the cenotes, because we've already talked about how hard it can be to get to some of those places. And it could be hard to see them because all that tree cover. What are the locations and physical characteristics and their relative ages? One of the characteristics of cenotes is how circular it is. If it's super circular, it's really young. If it's like chewed up and everything weird kind of shaped, it's old because it's been weathered, been degraded, okay? So we wanted to look at that. And then we could see how fast the cenotes are developing or degrading. And then what are the most vulnerable areas for cenote collapse? Sinkholes. This is in Mexico, actually. It just opened up last week, yeah.
Yeah, that was cool.
Yeah, 2 dogs were found in there, they rescued. I think by now his house has already gone in,
Yeah.
It's already collapsed.
and that's it.
All right, great, thank you. So, questions, Jackie?
Yeah, oh, many. Yes, I don't remember your name.
Gio.
Jim.
So you said the brighter red means like good vegetation, yeah, and then less red,
Yes.
okay, means unhealthy.
It can, well, yes, but you have to also know the difference that you're looking at trees versus shrubs. Shrubs might show up a little more of a maroon color. Grass might show up a little more pinkish.
Okay,
It depends on what you're looking for.
okay.
So you're saying that's why it's good to go in person to
Yes.
to verify that it's accurate.
Yes, because we have a resolution of only so much. So it might show that that sinkhole is 100 meters long. But we get there and it's 200 meters long because the resolution is so off, it can't catch everything because that box, that pixel, is only as big as this.
Now, does GIS like influence like Google Earth? Like why we
Yes.
have like these like beautiful like images of
Yes.
of an area.
Yes, it does. All that stuff is remotely sensed. due to private and public funding and private and public companies. So that could be like Maxar is one of the private ones that they use. They're a very fancy company. And Planet is another one. It's a very fancy company as well. So yeah, and then you got USGS, and the governments have webs that have satellites up there, remote sensing stuff. Sentinel is ESA, European Space Agency. NASA has some up there. So yeah.
So when you're looking at the aerial imagery, are you going to measure with the images that you have the size of the cenotes?
Yep.
You can compare them with like maybe Google or something like that, or?
No, we're gonna have my man Stuart and Alex, who's not here.
Yeah.
They're gonna go out there, not with a tape measure, but actual survey equipment.
Yeah,
I was gonna have them, do it the old way if that was the case. And they're gonna survey how large it is, how circular it is. They're going to see how deep it is, how degraded it is. And then they're going to take pictures of all the plants that are around it, see if that changes. Because I don't know yet, I haven't seen any research on vegetation around cenotes and health as indicators.
And so we just ordered the GoPro 9 so that it has the Hero, so we can get the fisheye lens, so that, and we have the new GPS unit that supposedly works for
That's what
vegetation.
he said.
And then we have all the survey equipment. So basically the thought is Alex and Stuart are gonna be doing all these measurements. You guys will be doing your, collecting microplastic samples. You guys will be surveying people, you guys, so we will go to a location and like, everybody will be doing your project in one location. And then we'll pick up and we'll move to a new location, and then and then if you're done collecting your sample, because microplastics, you take a jug and you're done, you have a lot of work to do when you get back to the house, which you don't have to do in the field, so you would help them out. And then in the evenings, while you're sitting there, having to work, they will help you out in the evenings. So that's kind of the thought here, is that we're gonna come up with some sort of like scheme with Jackie, that when we arrive at a location, you guys will have like, we have to measure this, we have to do this, we have to do this, and have like a checklist and collect all that data.
Yep, and I was gonna ask about photocopying their sheets so that they have that.
Yeah, and I have Write in the Rain paper up in my office.
Oh, okay, great.
So Write in the Rain paper is paper that doesn't, like if you get it wet, it won't deteriorate and the ink doesn't come off of it. And so I can make you photocopies of all your data sheets, or give you a notebook or a data
That's
sheet.
nice.
And then you can write into it, and if it lands into the cenote, you won't lose your data. It's very nice. So the Write in the Rain notebooks, these are yellow notebooks. They're yellow so you can find them in the field. B, they float. So if it does fall into the water, it floats to the top, and then you don't lose any of your data. We do have field notebooks for you all, so you will be getting your field notebooks when we get down there. So you will be getting notebooks.
I think in Phil's presentation, he pointed out a yellow notebook, I think.
Yeah, that's it. You guys will all get your Write in the Rain notebooks. So we have those for you. It's just, you don't need them right now.
Right.
But you will be doing that, and that's how you're gonna collect your data. And then I have note paper that you can put through a photocopy machine. So if you have a data sheet, you can actually just write right onto the sheet and then save all your data. It's amazing. Yes.
It's fantastic.
Okay.
Okay, any other questions before we split?
So what time tomorrow morning?
Oh, yes.
Meeting?
What time? What time you want?
I think that's fine.
Okay, you wanna do 9:30? Because I got a lot of stuff for you to do.
Yeah, as early as possible.
Go
Yep.
Santo.
Okay. Yeah,
Thank you.
Okay, so it is lunchtime. It is 12:30, so why don't we make it an hour lunch? You guys want an hour? So if you guys want to go somewhere and stuff, you want an hour lunch break? Yes, whatever you want. Yeah, an hour. You can grab your lunches. You can go sit outside. You can go whatever you want. You don't have to sit in the room there, but grab your lunches. You can do whatever you want. Be back in 313 at 1:30. That other room, be that room, because we're gonna be doing group discussion, and this room doesn't lend itself, this is better for lecturing, that room is much better for group discussion. So be back there at 1:30, you guys have an hour break,
Can we leave our stuff in the other room?
you can leave your stuff in that other room, I'm gonna be sitting in there and doing stuff, so you can leave it there. Anybody who's working with me, we're meeting at 9 tomorrow morning.
Oh, yeah, I know. That was an awful.